applications of integration, velocity, and net change. Suppose you are traveling along a straight highway and your position relative to a reference point or origin is s of t. And suppose your velocity is v of t, and t is greater than or equal to 0. Then your displacement over a time interval from A to B is the change in position s of B minus s of A. And this can be found by integrating the velocity function over the given time interval. Using integral notation, we are looking for the integral of the velocity function from A to B, and that gives displacement. So displacement is the net area under the velocity curve. If velocity is both positive and negative, then the displacement is the area of the region above the t-axis minus the area of the region below the t-axis. So we subtract the region above the t-axis. We go region above the t-axis minus the region below the t-axis. So while area is always positive, net area, just like displacement, can be positive, negative, or 0. For this curve, the net area looks to be positive since the area above the axis is greater than the area below. So displacement equals net area. What about distance? Your distance traveled is the total distance traveled whether your velocity is positive or negative. Distance traveled is the integral not of velocity but of speed. So you can see that the region that used to be below the t-axis is now above the t-axis because we're taking the absolute value of the velocity function, which is the absolute value of the velocity function is speed. So now distance traveled is the sum of the areas of all regions, whether they are above or below the t-axis. So displacement is region above minus region below. Distance traveled is region above plus region below. Let's find and interpret this integral given this velocity function and this time interval. The first thing we do is we set up the integral. I'm going from 0 to 3, and I also put in my velocity function. The next thing we want to do is we want to find the antiderivative. So let's just integrate. After we integrate, we evaluate from 0 to 3. After the dust settles on the arithmetic, we get a value of 0. Now, what does this mean? Our function given is a velocity function, and we're going from 0 to 3. We got a displacement of 0. A displacement of 0 tells us that the object returns to its starting point at t equals 3. So this was a round trip. Looking at this geometrically, the area of the region above the t-axis is equal to the area of the region below the t-axis. Also, let's notice a few things. The velocity of the object is 0 at t equals 1. The velocity is positive for the time interval from 0 to 1, and negative for the time interval from 1 to 3. Also notice if we integrate just from 0 to 1, we get 8/3. And if we integrate just from 1 to 3, we get negative 8/3. So the actual distance traveled, if we wanted distance traveled, remember that is the region above plus the region below. So we'd have 8/3 plus the absolute value of 8/3, a total of 16/3. So displacement is 0, but distance traveled is 16/3. Let's do a different example. A block hangs at rest from a massless spring at the origin. So when the block is at the origin, it's at position 0, and that's hanging at rest. Now suppose we take this block and we pull it down. We pull it down 1/4 of a meter, and we're going to call that the initial position. So at time equals 0, it's below the origin. At time equals 0, the position is -1/4. The block is then released. The velocity function is given by 1/4 sine of t. Find the position of the block for t equals greater than or equal to 0. Now, if we have velocity, then the way to find position is to find the antiderivative of velocity. So our velocity function is 1/4 sine t, and the antiderivative of that is -1/4 cosine t plus my arbitrary constant. Don't forget your plus c. Now, what is c? We're going to use the initial position, s of 0 equals -1/4, in order to find c. Well, if t equals 0, then my position function must equal -1/4. Remember that cosine of 0 equals 1, and so I have -1/4 equals -1/4 plus c, and that tells me that c has to be 0. So my position function is -1/4 cosine t. Let's graph both the position and the velocity function, and we're going to put them on the same t-axes. My position function, -1/4 cosine t, is given in blue. My velocity function is given in pink. Notice that they each have an amplitude of 1/4 of a meter, which is the distance the block was initially stretched. Notice that the position is equal to 0 when t equals pi over 2, 3 pi over 2, 5 pi over 2, and so on, if we kept letting the block go on and on. So it moves through the origin at pi over 2, 3 pi over 2, and 5 pi over 2. That's looking, and we find that by looking at the position function. Now looking at the velocity function, we can see that the block is momentarily at rest at t equals, well, of course 0, but then pi, 2 pi, and 3 pi. Let's finish up with an example from economics. A book publisher estimates that the marginal cost of a particular title is given by C prime of x, where x, going from 0 to 50,000, is the number of books printed. So C prime gives dollars per book. What is the cost of producing the 12,001 through the 15,000th book? Recall that marginal cost is just the derivative of the cost function. So having produced 12,000, the cost of producing another 3,000 is just the antiderivative of the marginal cost function from 12,001 up to 15,000. So we just put in what our marginal cost function is, and then we integrate and evaluate. And the cost of producing, if provided that you've already produced 12,000, the cost of producing the next 3,000 is going to be $27,000 and $27,900. So that's it for this section, and take care, and I'll see you in the next section.